if you can see it. Can you see it?
Screen is on backlash, I think.
Can you check on some lights? Check it works.
It's still bad.
Still bad.
Mm.
What about now?
Couldn't see.
I think we close this blind better.
Okay, we get lights. Check it.
Better?
No.
No.
It's still there.
Which is second. Can we go for?
Maybe then,
What about now?
would it not be better to put on that?
I don't know.
Try. Yeah, you could see it right here, but
What do we find out from the lights?
it's not like-
Too good?
No, it's. You can barely see the screen. I think just keep the lights off.
Right, okay, let's try this one.
No.
No, okay. And this one? Don't shoot this one.
Yeah, that's fine.
This one's fine, I think. Okay, I think it's
It's dark.
okay. Everybody, thank you for coming. We have a Zoom. He's from PSS, a company which designs outreach for headphones. Very talented people. It's probably the outreach headphones designed at PSS. We have research and development company, research and development factory here in London, and have multiple other factories in other countries. So it's a big international company. So today, we're going to speak about with all technical concepts. You like with high possibility you will see on the technical interview in the electrical engineering firm. So the floor is yours.
Yeah. Actually, today I will explain some to the point of some point that helps you guys if you are interested in analog circuit design or analog IC design, or if you are interested in nanotechnology, then yeah, today I will share some technical question and test some basic instructions that interviewer used to ask in an interview. Okay, I want to start with just a basic design flow, which I also discussed previously, I think on Saturday. It's like that. First of all, we can split the IC design flow in 3 to 4 steps. First of all, is the circuit design engineer. In every step, there are a couple of engineers. The design team, first of all, the concept of the idea mean however they want to design any circuit, they just consider some specification. Let's say for two-stage op-amp, there are a couple of specifications, there are a couple of architecture, which architecture they should to use, and based on the architectural specification, they implement the design, and after that, they also run a couple of simulation. This simulation is known as pre-layout simulation. And after pre-layout simulation, if they are agree, and only then they go for physical design. In this step, they basically the IC is designed in physically with the metal layers. And this is the job for layout engineer. This portion is for layout engineer, and they are responsible for to physically design the chip, whatever they guess in this person, as well as they also some verification, let's say DRC, design role check, or LVS, and couple of verification. After that, they do the parasitic extraction. And after this parasitic extraction, they again simulate it. This simulation is known as post-layout simulation. And if everything is good, going fine, then it go for fabrication. In fabrication also, they are not making thousands of chips in one time. They can make around 100 or 200 chips, and again they test it in their lab. And after it passed everything, then they will fabricate it in a huge amount for the customers. And this is the basic design flow. Anyone has any question in any steps there? I think no, because it's crystalline clear. But it's curious. Okay. Okay, then let's consider that some typical block diagram of analog system. Let's see, if you consider about any communication system, let's say this is the audio signal. If we take an example, then there's a preamplifier, and after that there's AM modulation. I think you've studied this course or this topic in several basic course. And then also some reference oscillators, and after that there is some power amplifier and this send using this antenna. And in the receiver side also, there is something in receiver, LNA is low noise amplifier. The job of this LNA is that whatever they're receiving in this receiver side is very noisy. To reduce the noises, after that there are a couple of steps, such as there is analog signal should be converted into digital domain to process or whatever. This is the typical block diagram of analog communication system. And here you can see in every steps we need the amplifier design. And if you also consider about one more example, let's say this is the recording system. In ECG recording systems, this is also a typical block diagram where you can see there is some electrode which is attached in our body, and after that there is some special instrumental amplifier and low pass filter, notch filter, sampling buffer, couple of stages. So I want to give you a message that is that amplifier is the backbone of every analog circuitry, and every analog circuit you will find this amplifier. So in interview you will expect a huge question on several types of amplifier. Let's say common source amplifier, common drain amplifier, operational amplifier. Even if there are a couple of operational amplifiers, let's say two-stage op-amp, telescopic op-amp, folded cascade op-amp, and so on. So you have to study amplifier very well. This is some KVL and KCL equation. I'm not interested to visit there. I just want to give you a message that to design an amplifier, we need something which can produce a current. If you go through the basic circuitry and how an amplifier works, you will find that, let's say, if I calculate KCL in here, you will find that the output and input relationship, which is also known as the gain, and the gain is minus KRL. Which means in this circuit we can see that we need something that can produce a current depending on the voltage. And the BJT, MOSFET, these two devices is also known as voltage dependent current source. These devices can produce current depending on voltage. So this is the message I want to give you. Okay. Now, yeah. I'm do it. Okay. Can someone else? Thank you. Okay. In interviews, sometimes they may ask what is channel length modulation. So if you are interested, you can study this topic. I will not discuss it here, but yeah. Here, let's say we are taking an example with MOSFET. This is a MOSFET, and let's say it is a mic. And first of all, ignore this voltage source. There is no voltage source. It's mic, or it may be an audio signal. And yeah. So to amplify this audio signal, there might be 2 or 3 conditions. But to amplify it, first of all, this a transistor has 3 operating points. One is off or cut off, one is triode mode, and one is saturation. You agree with that? There are three operating points of a transistor. And to operate it as a voltage dependent current source, we need to operate this transistor in saturation condition. To make this transistor in saturation, we need this biased voltage. There are a couple of factors and equation you will find in your textbook or basic courses easily, that how we can operate this transistor in saturation. And wherever this transistor in saturation, and even in that condition, if you apply a voltage there, then it can amplify. You expect an amplifying signal here like this. Let's assume an example. Let's say the output voltage, this voltage may be 100 millivolt, or whenever there is no signal, there is no mic signal. Let's assume due to this voltage, your drain current is 1.7 milliamp. Just assume it. And if you applied a voltage 10 millivolt, mean if your mic is producing a 10 millivolt AC signal, then if you can expect that a huge change in there, the drain current will huge change is there. And if you assume this difference, it might be around 780 millivolt. Can you go? Okay. Okay. Mean, I studied about, I think you have about idea about transistor, right? MOSFETs. Are you familiar with this curve?
Yes, we could go first.
Yeah. Because in MOSFET, there are several types of characteristics curves. Let's say, a MOSFET. Yeah.
I can write something. Yeah, sure. Oh, yeah.
If it is transistor, it is a drain. Let's say it is a source terminal and it is gate. Okay, so there may be two voltages. One is VGS, gate to source voltage, and another may be VDS, drain to source voltage. So we can see there are two voltages, but we cannot change two voltages simultaneously. We need to keep one voltage fixed, and then we can change this one. And if you fix this one, then we can change this one. Then in these two conditions, we will expect two different type of curve from here. And then we also can see that what are the impact of if we change the VDS as well as if we change the VGS. This curve here you can see here my VDS, my drain to source voltage is fixed. If my drain to source voltage is fixed, and if I increase this VGS gradually, then if you simulate it in any software, you will find a curve like this. This current is my drain current. This current, the terminal current from this drain, this current is shown like this. Okay. An interview, if you go, you definitely expect that they will ask about this curve. And what is the meaning of this curve? There is a specific meaning. Okay. Before explaining this curve, I want to go down and right there. Okay. Can you go down? Down, down, down. There is another curve.
Yeah.
Yeah, this curve. Okay, this curve. Okay. Let's say now if I make this VGS constant and if I vary this VDS, then I will find a curve VDS as ID like this. So this curve giving us some messages, and this information is really necessary for us to design an amplifier. First of all, we have to consider this curve. As I told you that to operate a MOSFET as a voltage-dependent current source, which we need to design an amplifier, so we need to operate the transistor in this point, in saturation point, because in this point you can see this curve says if we change voltage, we know that MOSFET is a voltage-dependent current source. If we change the voltage, the current will increase. But after some point, this current will not change. It's ideally constant. So we need to fix our transistor in that point. So from this characteristic graph is depending on which circuit you are designing, and you have to find this point that what is the accurate voltage of VDS where my transistor operate in saturation. Let's say it is 800 millivolt. You find that in 800 millivolt, your transistor in saturation point. Then you have to fix your VDS. You remember I fixed a VDC voltage there. The VDS in 800 millivolt. However, there is other point which is known as threshold voltage. My transistor will turn off before this threshold voltage. Let's say if this threshold voltage is 100 millivolt and if I applied 90 millivolt in the gate, but still this transistor will be off. It's work like a switch, an off switch. However, in this linear mode, my transistor work like a resistance. But we are not preferred this reason. We are interested in there. First of all, to design an amplifier, my transistor operating point should be there. Now can you go up, please? Yeah. Now let's say you can assume that in 750 millivolt, my transistor reaches at saturation point. But now you have to consider that if you are okay with 750 millivolt or not. I'm drawing here. Let's say this is my saturation curve, and I find that this is, let's say, 750 millivolt, and it is guaranteed that whenever I apply greater than 750 millivolt or 750 millivolt, my transistor is saturation, I'm okay. But depending on how much gain you want, there is another term which is known as transconductance. A transistor can provide more gain if it has higher transconductance. So the circuit designer, they need higher transconductance, because if I can increase the transconductance, then my amplifier is strong, my MOSFET will be strong, and it can provide more gain. And to get a stronger transistor, we need this curve. If we fix VDS and if you play with the VGS in the saturation condition, then we will find like this. And this curve says that I can expect whenever I expressing some formula, then you can see that if my ID, drain current, is huge, then my transistor is strong. It can produce more gain. So I need to push my circuit in this way, in this point as much as this, because you can see it can provide more current there. This is the significance of this curve. And in addition, as it is known as the GM, which is known as transconductance, and the unit of transconductance is Siemens. And you can go a little bit down. And the definition of transconductance is that a little bit change in the ID curve. If it's delta, if I change a little bit in VGS, then there is also a change in my current ID or IC, what you say. It means that this curve is not linear, it's an exponential curve. So this is the mathematical expression of GM. So I think you understand that why this GM is important, because this GM is important to get a higher gain. To set my operating point, this curve will help me, along with, you can see that how our transistor can operate in saturation condition. You can put down here. Okay, and yeah, there's also a question that why we need the biasing. We need biasing for two purposes. First of all, this biasing point determines my transistor in saturation or not. If you look at this curve, this is my DC biasing. We have bias circuit like this. It is saturation. And the second point is that I have to buy a circuit like this, it can provide more gain, whatever I can expect from it. Okay, can you go down please? I think we explained this one. Yeah, one good point. Then this is another interview question. You may ask that, as we explained that this curve is ideally constant, but due to the channel length modulation, this is not a straight line. You can find, if you zoom there, you will find a curve like this. So interviewer asks that why this curve is upward trend. This is due to channel modulation. If you study this one, then you can find why this curve is like this. Okay, and yeah, this is the just separating operating condition. Let's say here my VGS is constant, and if I increase the VDS, yeah, definitely it increases my current. Let's say here if VDS is 1 volt, here VDS is 2 volt, and here VDS is 3 volt. If I increase the drain voltage, my current also increase, and my saturation point also move like this. If I all this curve like this, if I increase my VDS, it will go like this, and my saturation point also go like this. Okay. Okay, go a little bit up. Yeah. This is the 3 important graph. This 2 graph we already discussed. There is another relationship with GM and ID that, as I explained, that if we need higher GM, we have to increase the ID. This is ID versus GM curve. And yeah, where you can see if we want to more GM, we need to increase ID. There is some basic relationship. I can also provide this slide or PDF. You can collect it. Can you go down? No. There is some expression. Yeah. You have to remember this 3 expression, because this 3 expression is very helpful. And interviewer used to ask, can you write any mathematical expression for the GM? And from this expression, you can see that basically whenever you're designing any circuitry, you need to play with the circuit. Then how you can play? Let's say, as I claim, we need higher GM. Then how can we increase GM? We should know which parameters are related to GM. You know what is mu n? Anyone? No idea what is mu? Okay, no. Yeah, basically, this mu and CUX, this is a technology-dependent parameter. Due to the several process, which process they are using to fabricating the chip, this is not in our hand. You can say this is constant. We can only change the width and length of a transistor, as well as we also can, this with threshold voltage, this voltage also constant. We cannot do anything with that, but we can play with the VGS. So these are my thing that I can play with GM. So if I assume this point is constant, then you can see my GM is proportional to this value. There are also some more common expression with GM, and this one is very much popular. This the circuit designer, they are using this expression too many times. And where you can see, if you assume 2 mu and CUX WYL, everything is constant, my GM is proportional to root over ID times. So can you go down a little bit? Yeah. So by taking all of this assumption, let's design our amplifier, first amplifier. Anyone studied analog circuit course or? Yeah, if you're familiar with this circuit, this is common source amplifier. There is several types of amplifier: common source, common gate, common drain. But typically, the gain of the common source amplifier is higher than the rest of the 2. So therefore, I'm discussing the common source amplifier. Okay, if someone drawing a circuit and asks you that, how can you identify what is the name of the amplifier? It's typically that this terminal, the input is connected to the gate, the output is connected to the drain, and the source terminal is open. There is nothing. So it is the common source. let's say if I want to make it common drain amplifier, then my output is connected here and drain will be open. There is nothing or other connection. So it is the common drain. Okay, whatever. So there is another more popular analysis which is known as small signal analysis. So I highly recommend you that please study small signal analysis, because in interview, I'm guaranteeing that the interviewer asks you about draw a small circuit like this, whatever, and they will say draw the small signal model of the circuit. And you have to know how to analyze small signal models. Here I'm not discussing anything from small signal model, but there is a calculation of from small signal model from the output by input ratio. This is the gain of the transistor or this amplifier, and the gain is minus GMRT. How it comes? It comes from small signal analysis. So if I ask you that how I can increase the gain of the amplifier, how can I increase the gain? Yeah, we can increase the RD or either we can increase the GM, right? There is two parameter. Let's assume that let's say you can see here, right? This is my amplifier, this is my input, this is VDD, this is that's the RD, and here is GM. Okay, this is my output. So my equation says if I increase the RD, then I can increase the gain, right? Okay. To operate this transistor in saturation, there is a condition which is that my drain voltage, this voltage, my drain voltage, VDS should be greater than or equal to VGS minus threshold voltage. So this is the condition to we can operate a transistor in saturation. So you can see this voltage should be greater than this value. This value also known as overdrive voltage. Interviewer may ask, what is overdrive voltage? Overdrive voltage is nothing but VGS minus VTH. Okay, now you can think that if I increase this resistance RD, it increases my IR drop here, right? Isn't it? It increases my IR drop. It means this point, the voltage of drain will decrease. Let's say here is 5 volt, and this is the, what is this Vout? Vout is nothing but VDD minus IDRT, right? VDD minus RD, and this drop and this voltage, right? If I increase this resistance, then this drop will increase. Ultimately, this point will go down. If it breaks this condition, then this transistor will go in triode region. The curve I discussed, it will not in saturation, then it will not work. So there is some limitation. I cannot increase this resistance too much. Along with, if you can see some formula of GM, there is also some limitation. We cannot expect a huge gain from this circuit. The typical gain of a common source amplifier is 5 to 10 dB. But however, here I explained that we can increase RD and ID, but there is some limitation. Okay. One more important question sometimes they ask in interview that what is FT of a MOS? I will not discuss, just I give a hint. There is something known as FT of a transistor. Please go search online. Go down. Oh, no. Okay. Then what is the maximum gain of this circuit? So the maximum gain I can find from this circuit that if I replace this this resistance with a current source. This is a property of a current source. The output resistance of a current source is ideally infinity. It means a huge resistance a current source can provide. So a current source may provide you 50K, 60K, 100K, huge currents. And whatever the gain we can find from this circuit, it is known as the intrinsic gain or the maximum gain of this circuit. So what is the solution? We can replace this resistance with a current source. Why we replace it? Because the output resistance of a current source is ideally infinity, and we will get the maximum gain from this circuit, which has a special name. It is known as intrinsic gain of a common source amplifier. If someone asks you what is the intrinsic gain, it is the maximum gain which I can find from this circuit. How we can find it? Just replacing this resistance with the current source. Okay, and if they ask you, okay, how we can design this current source? We cannot buy it from market, right? We have to design this current source. Okay, it's simple. We can use a MOSFET here, right? And if we operate this MOSFET, we need an external biasing voltage for this. If we operate this MOSFET in saturation mode, this MOSFET will work like an ideal current source. Remember, I showed this curve. In this point, this transistor work as a current source, and we'll find it. And it is known as the cascade structure.
Cascade? Cascade.
Cascade
Okay.
or cascade something.
Okay.
But there is two chapters. One is cascade and one is cascade.
Okay.
That you can study, and there are also some advantages of cascading and cascading. Okay. And yeah, the output resistance of a current source is generally they defined it using RO. This is the term they define the output resistance of a current source. Can you get down? Okay. There are there are a couple of books. Let's say one book from Bayezid Razavi, Introduction to Analog IC Design. One book from Ken Martin. I also provided the book reference to him if you want to collect him. So in those books, you will find there are several versions of this circuit. And in interview, you definitely ask some question that, let's say here, you see the resistance, then I replace with a transistor. I also can replace with a diode connected device. This is a diode connected device. The gate and drain is connected. It is known as diode connected device. And there is also some small signal analysis from, let's say, just assume this diode connected device. If you just draw this diode connected device and if you do the small signal analysis, you will find that the output resistance or the equivalent resistance of a diode connected device is 1 by GM. So you have to go and study the small signal model for that. But so what is the gain of this circuit? The gain of this is first of all, this is a common source amplifier. The gain of this circuit is minus GM RD. And what is RD here? Here RD is 1 by GM2. 1 by GM2. However, if there is no channel length modulation, I assume there is no channel modulation. Okay. This circuit has some advantages. What advantage there? You can see here the gain of this circuit is only depends the ratio of two transconductors. Can you go a little bit down? And there is also some simplification. If you using the there is a couple of formula of GM. So if you put this formula here, one of this formula, and then there is some constant mu and Cux WL something was there. So mu and Cux, this is the constant. So it will cross from up and bottom and only left the WL of 1. It's mean the gain of this transistor only depends. Let's assume one more condition. This L and this L are similar. The length of this two transistor is similar. The gain of this circuit only depends the rotor W1 and W2. The width of this transistor. It's mean this is an advantage. What type of advantage? There is no environmental dependency. What is environmental dependency? Let's say if it is in resistance, the property of resistance may change depending on temperature. If you increase the temperature, reduce the temperature, the property will change. In addition, the mu and Cux. I also told that this mu and Cux, it is a process dependent parameter. It will change its property depending on wafer to wafer or technology to technology. But in this circuit, there is nothing. There is only depends on the width of the transistor. So this is the beauty of this circuit. And the voltage gain of this type of circuit will be more stable in different conditions. Leave it down. Okay. There are some common factors which can affect our gain. Let's say temperature variation, as I told. Due to the temperature variation, my mu n and mu p. It is also known as the mobility, the electron mobility. The electron mobility is also known as the mu n mu p, and supply voltage variation. If you change the supply voltage, then also my circuitry might. If I change the supply voltage, my drain current will be changed, right? The drain current. If the drain currents change, it affects our GM. You see, the GM is also related to drain current. Eventually, the entire gain of the circuit will change. Along with the process variation, we cannot change it because it differs wafer to wafer. And here there may be some signal distortion because analog signals are very noisy and it can easily be affected by noise. They are very sensitive. Okay, so there is a little bit improvement of this circuit. Here I am showing just few common circuits which we need to design and to stitch open. There are several versions of this circuit. I am not mentioning here, but I am claiming you that in interview they may ask you any circuit, and they may find you that, let's say, what is the input resistance of that circuit, what is the output resistance of that circuit. Let's assume they draw a circuit like this, and they tell you, okay, find the input resistance of this circuit, find the output resistance of this circuit, what is the gain of this circuit. So in your textbooks, you will find several versions of this type of circuit. Okay. This circuit also has a special name. Can anyone say me what is difference in this circuit from previous one? Like this one, there is any difference?
RS.
Yeah, the only difference is RS. Previously, this source is directly connected to ground, but now this source is connected with a resistance and then it is connected to ground. And this circuit is known as common source amplifier with source degeneration. Source degeneration means source is not connected to ground. There's maybe current source, some MOSFET, something, there's something there. And the voltage gain of common source amplifier with degeneration this is the voltage gain equation. It is minus RD divided by 1 by GM1. GM1 means this transconductance of this plus RS. And if there is some simplification, I'm not going in mathematics, but you will find an equation like this. It means the gain of the circuit only depends on these two resistance. And obviously in temperature change, the resistance will be changed. In here also the same effect. It will change this property, this one also changes property, and then it cancels each one. And in this way, there are no process dependency as well as the voltage gain source here more stable. Okay, you can go down. Okay, let's say we can replace this. Previously there was RD, but now I can replace RD with a diode connected device. And if I tell you that find the output resistance, find the gain, is super easy. Can you go up? Yeah, It's a general formula. It's a general formula, and you have to remember this formula. This is the minus RD divided by 1 by GM1 plus RS. If you remember this one, then if you go down, please. Okay, so RD. But here, what is RD? RD means the resistance of this one. And as I claimed that the output resistance of a direct current device is 1 by GM2. So I can replace 1 by GM RD with 1 by GM2 and everything is same. Okay. Okay, what I said that, yeah. There is no current flow through the gate terminal. There is no current flow. If I draw a cross section B here, there is an insulator, silicon dioxide, in the gate of a MOSFET. And due to this insulator, there are no current flow there. So therefore, the input resistance is 0 because there is no current flow. But, sorry, input resistance is infinity. There is no current flow, mean it's infinity, it's huge. But, yeah, but it's at low frequency. At higher frequency, there will be some parasitic capacitance. There will be some, I'm telling you, a MOSFET, there are a couple of parasitic capacitance. And if you study the Miller theorem, you can find this existence of parasitic capacitance. And yeah, at high frequency, we have to consider this parasitic capacitance also. But these types of questions are very common in interview, and they used to ask, find the input resistance, output resistance in different conditions, as well as the small signal model. Let me go down. Okay. Now let's talk about differential pair. So, what is this circuit? This one? No, only this circuit. Only this portion. Common source amplifier. So we can see this is a common source amplifier, and this one also a common source amplifier. There are nothing but just consider the half circuit. Let's say the half circuit, it's a common source amplifier. And here, the source is not connected to ground. There is something there. It's a common source amplifier with source degeneration. You got it? So my motivation was to design this differential amplifier. Therefore, I started from some basic curve of amplifier. Then I discussed the common source amplifier. Then I explained why we need this current source here instead of an RD. Then I explained some advantages of source degeneration. Then I come here in differential pair. Okay, there are some advantages of differential pair. Anyone knows? Basically, this differential pair can reduces the common mode noises. Okay, I'm explaining what is common mode. This is the biasing point. We need this biasing point. Can you tell me why we need this biasing point? Why we need bias there?
To allow the transistor to function.
Yeah, to make this transistor in saturation and to make the transistor in higher GM. There's two motivation. We need higher GM as well as my transistor should operate in saturation. In this way, we will fix the bias point depending on the designer. And this DC voltage, let's say if it is 800 millivolt, so this 800 millivolt should be applied here and here, the same voltage. As this voltage is same in both cases, it is known as common mode voltage. It's common in both here. So I am replacing this BDC with the common mode. And here, we have to apply a differential signal. What is differential signal? It's also a common question in interview. A differential signal means, let's say, you have different color. If it is V, sorry. Okay, let's assume this blue color is V1 and the red is V2. This V1 and V2 is nothing but these two voltages. Okay, and this is the condition of differential signal, that if the maximum point less than it is 5 volt, then it should be minus 5 volt. And the frequency of this signal should be same, mean every point should be same signal, but out of phase. There is a phase difference 180 degree. This is the differential signal. So if we applied a differential signal here, then analog signals are very environmental noisy. So if any noise comes here, then the beauty of the circuit is that this circuit internally work like this. It can reduce the noise. It can subtract the common mode noise. So we need this types of differential amplifier to deal with analog circuit. I think you have remembered that beginning of this presentation, I give you some example of some block diagram of analog system. Let's say ECG recording system. The frequency of human body signal is, I think, less than 2 or 3 hertz, and the amplitude of the ECG signal is 500 to 600 microvolt. And whenever we are dealing with this type of signal, it's too much noisy. Let's say you are connecting some electric wire there, so noise comes from anywhere. So this differential pair can reduce this noise. However, there is also some filtering process. So therefore, we need these types of differential pair there, as well as this differential pair also can provide more stable voltage gain, and the voltage gain of a differential pair is obviously higher from just a single stage amplifier. So this is some common advantages, and there is special name of this source, this current. It is known as tail current. This current source is used to known as tail current, and it is the source degeneration. And if it is 1 milliampere, then it would be 500 microampere. It would be 500 microampere. This I total is I1 plus I2. Is always same. If my V1 is greater than V2, it is possible that more current flows here, less current flows in this branch, but the total current should be equal to this one. This is some analysis. Again, if you go to the textbook, you will find some mathematics of differential pair, how to design. There are some formula. So if you do this maths, is very helpful for you, then you can understand it easily. And now if in practical, how can we design this one? There are a couple of structures. Let's say this is one of the most common structure. Now we have to design this I1 and I2, right? So for it, you can see it is in current sources. So this transistor should be operating in saturation, then it can work like a current source I1 and I2 like this. And if you consider only this structure, it's a current meter. Just this M1 and M2, it is a current meter. And this is my differential pair M3 and M4. And we also can design, we have to design this one with transistor, means we are replacing everything with transistor. And don't worry about the structure, because in every company they have structure, they have everything. You have to just change some property and make some improvement in the circuit, just that's it. And yeah, and it is also a current meter. This is my reference current, it's coming from here, then it is mirroring here, and it go in this two branch, and it's the output. So, and yeah, this is also known as, can you go up? This is also known as a single stage differential pair, and there is single inlet output. There are some special circuit that you will find there are two outputs, one output from here and one output from here. Let's say there is another circuit look like this. There is no connection between these two. Let's say a symbol. V1, let's say it is V2, and there is output. Let's say it is output 2, let's say it is output 4. It depending on the application, depending on the architecture, they are designing several types of differential pair. Yeah. Sorry, assume this example that in this is a recording signal, this differential pair can reduce the common mode noises. And this is the current meter, as I'm telling you. This is the basic structure of a current meter. And this is the one typical formula how this current is metering. Let's say a current meter, if anyone asks any question about current meter, you have to remember 3 to 4 points. One point is that, this is the condition of a current meter. If you want to design a current meter, the VGS of two transistors should be equal. The gate to source voltage of this transistor and this transistor should be equal. And same, the VDS of this two transistor should be equal. And the channel length of this two transistors should be equal. If it working in this condition, then we can amplify our current depending on the width. Let's say we can double our current. If our reference current is 1 milliampere and the width of this M2, if it is double from M1, then the current also will double. If it is half from here, then the current also shrink by half. Okay. And this is the NMOS current meter. You can see these two are NMOS. Are you familiar with, I don't know, what is the difference between NMOS and PMOS? No idea? No, it's very important. You have to know what is the NMOS and PMOS. The basic difference is that, the NMOS is always connected to the bottom side, the ground side. NMOS is also known as, I'm telling you, NMOS is known as pull-down device. Pull-down device is mean if you have two signals, 0 and 1, you have to use NMOS because NMOS can pass this 0 voltage very well. On the other hand, PMOS can pass logic 1 very well. Therefore, PMOS is known as pull-up device. Let's say there are two switches, right? Be out. When this switch will be on, this VDD will go there, right? This positive voltage will go in output. And when this switch is on, this 0 voltage, let's say it is my 0 voltage and it is my positive voltage. This switch is on, my 0 voltage is go there. So I should use NMOS here and PMOS here because PMOS can pass this logic 1 or logic high or positive voltage very well compared to NMOS. And this is the one main principle. And if I want to turn on an NMOS, we have to apply logic 1 here. Sorry, logic 1. logic 1, meaning we have to apply here a logic 1. But if we want to turn on a PMOS, we have to apply here 0 volt. If we apply 0 volt here, then it will just turn on. And if I tell about the symbol, the source terminal of NMOS is in this side, though this arrow is there, but for PMOS, the source terminal is there. If I draw a typical inverter like this, you will see this is an inverter, this is my NMOS, and this is my PMOS. So yeah, so sometimes we have to need copying current not only from ground level, something from the top level circuitry. So in this case, we may need the PMOS circuitry. You can see this is connected to VDD and it was connected to VSS, and it is copying current depending on other condition. Can you go down? Yeah. As it is a current mirror, so this is also known as current mirror load, and this is also known as differential pair. This is tail current, and here, as I explained, that what is differential signal? Differential signal is this. It has a same common mode point, and here from here it is going like this. This is the differential pair, and if it is not like this, then it will not differential signal. A differential signal should be like this. Can you go down? Yeah. To design a differential pair, we need a couple of equations, some formulas, by which we can easily find out in our textbooks. So in our textbooks, we will find it easily, and we can design a pair. And yeah, there is also some op-amps depending on our application. Let's say telescopic, folded cascode. Yeah. There is also another term which is known as frequency analysis as well as pole and zero. I hope you are familiar with this term, pole and zero. So in every analog circuitry, there is some pole and zero. So if you study in your textbook, you will find a separate chapter for frequency analysis. In this frequency analysis chapter, you will find this topic very well. And each topology, it has some advantages and some disadvantages. Let's say one disadvantage of telescopic op-amp, it reduces our voltage swing. You know what is voltage swing? No. Voltage swing means in telescopic op-amp, yeah, there are a couple of stages like this. Forget about the structure. Let's say here is your output, okay, and here is VDD. If you just simply consider like that, if you consider it is a resistance, it means there are some drop, right? There is a drop for this resistance, there is a drop into this resistance, and we will find some voltage here. So it's reducing voltage swing mean it reducing, let's say this point was 2.5, it reducing 2.5 to 2 volt. Swing mean this one. How much? What is the peak value? The swing will reduce due to this drop. This is the disadvantage of telescopic op-amp. Can you go down? Yeah. And this is a two-stage op-amp. Previously, you see only this portion here. It is a single-stage amplifier, and here this is the second stage. And here you can see this is my input. This input is going here, and output is coming from here. And this is nothing but a current source. I mean, if I draw this circuit here, it is look like this. It's a PMOS. This is my input, and this is my output version. And you can see the input is connected to my gate, and output is connected to our drain. And source terminal is open. There is no input and output. Therefore, it is a common source amplifier. This transistor is working as a common source amplifier. Okay, and here we will get more gain because first stage it has a gain, and the second stage it also has a gain. And let's say if this gain is AV1, this gain is AV2, the total gain will be AV1 multiplied with AV2. So our gain will increase. However, in two-stage op-amp, there is some compensation. We need some compensation, resistance, and capacitance to ensure the stability. I'm telling you, there is another term also known as gain margin and phase margin. Let's say there is another term, phase margin. It's indicating that typically the phase margin should be greater than 45 degree. Mean if phase margin is less than 45 degree, then we will not get stable voltage in output. We will find something oscillating, not stable. To find the stable output voltage from here, we need a phase margin should be greater than 45 degree. In industry, they try to keep it 60 degree or 70 degree. It's a different story. You have to study there what is gain margin and phase margin and how it improves our stability. And I'm telling you that I can play with this phase margin using this resistance and capacitance. This resistance and capacitance helps us to make our circuit more stable. How we do that? Go book and study about this differential amplifier. You will find a nice explanation. Okay. What is there? Okay, now assume you have a differential amplifier, and a differential amplifier, it has some property. Let's say open loop gain, it should be high open loop gain, is phase margin, is gain margin, is ICMR plus and minus. It's ICMR plus mean, okay, yeah, as I tell you that there is a certain point, and after this certain point, my transistor will be in saturation. But in this case, let's say, I tell you this curve, right? After a certain point, this curve will be in saturation point. But in this case, what will happen? It is a range. Let's say you transistor, not only can you go the entire circuitry, okay, not only these two, this full stage, every transistor here should be in saturation. Let's say you will find that the minimum point is 500 millivolt. In 500 millivolt, every transistor in saturation. Then you are increasing this voltage. And let's say in 1.2 volt, you find that, this transistor goes in triode. Then you have to operate in your transistor, all of this transistor in 0.5 to 1.2. Because if you go beyond 1.2, these transistors may not in saturation. So there is some designing parameter, and yeah, there's also some formula that how can you calculate this value. So from here, the designer is to calculate this one. Can you go down? Nothing more? No? Okay, let's go. And this is the design methodology or one common typical circuit in the analog industry. Have you any question after this one? No? Okay. And yeah, I'm also mentioning that please study about what is gain margin, what is phase margin, how to design that, and please study for Bajit Razavi book. This book is very good, and you will find a nice explanation there. Okay, now I would like to design, nothing design, just some general discussion about the PLL. because this parallel circuitry is very common. But if you also have any problem, you can bring it this side to see. This parallel circuitry is very important, and in job market it also has a high demand. So if you like this project, you can work on this project, and yeah, you can gain some basic knowledge on this circuitry. If you can write it in your resume, you work in a parallel circuit, I surely you will get a job. But you have to understand how to design it, how it works. So here, I will just explain some block diagram level. Nothing in depth, nothing. So first of all, my question is, why we need parallel? First of all, we should understand that. And yeah, in every stage, let's say to designing a BCU, you will find current mirror. Here you may find current mirror differential pair, depending on the architecture, as well as yeah, it can be designed using digital circuit along with analog circuit also. But the differential pair current mirrors, these are common here. It is a digital circuit. So therefore, you can see there is some analog blocks as well as digital block. Therefore, it is called the mixed signal. First of all, we have to know what is PLL, why we need it. Any idea about the phase law group? Okay, I'm telling you. Any idea about crystal oscillator?
Well, actually, but
Okay, no problem. You can see these are the crystal oscillators. It can generate some oscillating signal. These are the crystal oscillators. But
Is it basically a clock?
yeah, it's generating clock. But you can check your mobile phone. It may be working 2.4 gigahertz in huge frequency, or in the radio transceiver or receiver, they are transmitting signal high frequency that are not in megahertz, in gigahertz. But in market, there is no oscillator which can provide 15 gigahertz, 16 gigahertz. So if we need high frequency signal, then we need clock, high frequency clock. It should be more stronger than crystal oscillator. So my clock should be higher. It should be in gigahertz range, as well as it should be stable. There are two conditions. It should be in gigahertz range and it should be stable. Okay, but we have crystal oscillator. The crystal oscillators are stable. We have two oscillators. One is crystal oscillators, which is stable. We have one more oscillator, which is VCO, voltage control oscillator. It means that we can control this frequency using voltage. If you increase the voltage, you can find a huge frequency from here in gigahertz level. But VCO is not stable. This VCO is not stable. Even if a slight difference in the input voltage, the output frequency of VCO will change. For example, a radio station or every mobile company, they have a particular bandwidth. And if our clock circuit, if our clock speed will change, then my signal will not in that bandwidth. It will change its bandwidth. So we need something closed loop system that can produce high frequency and stable. So PLL is the circuitry which can produce ultra level high frequency along with a stable frequency. Okay, this is the motivation of PLL. And here you can see the reference. This reference is nothing but a crystal oscillator. It may be a crystal oscillator, and here we have VCO. This VCO can provide high level frequency. So how can we design it? first of all, it's clear, right? Why we need PLL? We need PLL to generate a gigahertz level frequency, as well as we can change our frequency depending on the input voltage. We can produce several band of frequency. In this projector, there is also a PLL. Okay, however, so how to do that? So first of all, there is a circuit which is known as phase and frequency detector. Forget about the architecture. What is the job of this circuit? The phase and frequency detector. Let's say you have a signal like this. Let's say it is a signal, and you can see the rising time of this two is not same, as well as the fall time also is not same. It means there is some phase difference. These signals are not ideal. Ideal signal means it's not like this. There is some phase difference. So the job of this PFD, it is that to find any phase difference in reference and the feedback. Forget about whatever the feedback. The job of this circuit that it determines is there any phase difference or not. Is there any frequency difference or not? Let's say I am designing this VCU for 2.8 gigahertz, and if it is changed from 2.8 gigahertz, let's say it makes 3 gigahertz, then the job of this circuit that it determine, oh, there is a change in this way, it play a role like this, then it will come back again 2.8 gigahertz. Okay, and yeah, and after that there's up and down signal. This is a charge pump. There are several architecture of charge pump, but if I draw the block level diagram is that depending on the up and down signal, how can we find this up and down? This up and down signal is generated by this PFD depending on it is same frequency or not. If there is any frequency change or any something, we will find some up or down signal. Up mean increase the frequency. If it's let's say somehow it makes 2 gigahertz, then this up signal manipulated like this, that it increases the frequency. And let's say it makes 2.8 to 3 gigahertz, we need to down the frequency. Then it will generate a down signal that somehow it makes the frequency down a little bit. So this is the job of a charge pump. Depending on this, it will producing some current from up or down. And there is a loop filter. The job of this filter is that it is producing an error voltage. This is a voltage control oscillator. So to maintain 2.8 gigahertz in output, it produces a error voltage. That this error voltage can fix this VC tuning range. You got my point? Let's say if any change in frequency here, it adjusts error voltage like this, that it can come back again here. So this is the beauty of this closed loop circuit, and there is a frequency divider. Let's assume here it is 100 megahertz. Okay, and you are expecting in this frequency 1000 megahertz, but you have to design this divider such like that after dividing it should be 100 megahertz. If it is the job of this PFD that it is always comparing this signal 100 megahertz or not. If it is increased from 100 megahertz, it do something. If it is reduced from 100 megahertz, it do something and it adjusts it again. So what should be this divider? It should be divided by 10, right? I have to design it divided by 10, then it will divide it by 10 and we will find 100 megahertz again here. So this is the beauty of the PLL. and you can work in this project. It's very good. If I tell a little bit something about what is VCU, there are several structures of VCU. The one common structure is that, what is it? It is inverter, right? If I connected three inverter like this, okay, assume three inverter like this, and if I apply 1 volt here, what is it? Is 0. Then again it is 1. Again it is 0. This 0 again comes here. Then it's 1. It's 0. It's 1. It will continue like this. It means it produces an oscillation. This inverter produces an oscillation. It will oscillate like this. Yeah, there is also some formula. Depending on the formula, I mean how many stage we need, we can play with this. And there are also some other structure. Let's say we study about common source amplifier, right? Let's say it is a common source. We also can design oscillator using common source amplifier. The same structure, and just this output is connected here, output is connected here. This structure will also work like an oscillator. However, in industry, they are preferring this inverter as an oscillator because its performance is really good compared to common source-based oscillation. However, here we can see it generating a fixed oscillation. There is no change. But in the VCU, there is also some control circuitry from here and here, which can adjust the voltage. And depending on this control circuitry, it will produce a oscillation like this, which depends on the voltage. So there are several structures. You can study it. This is a good project. You can work on there. You will gain some knowledge. Even if it's not possible for you to work on full PNL, you can study this VCU. And as well as you also can study on this charge pump. And if you can add in resume, you can explain how it worked, what you did. It will be a value for you. I mean today. Have you any question? Nothing?
I'm supposed to ask you the voltage divider.
Sorry.
The voltage divider.
Yeah, this is the VCU voltage control oscillator.
The one.
This one?
Yeah.
This is the divider.
Sorry, the divider.
Yeah.
Is the design specific to?
Yeah. It should be designed like this. After dividing, these two frequencies should be same. This is my phase in frequency detector. And let's say if it is 100 megahertz, then if let's say it is 1000 megahertz, we are expecting an output. So we have to design this divider like this, that after dividing, we also get 100 megahertz here. Then it can compare, okay, it's change or not.
Okay, so let's say at the output it was like 800 megahertz instead of 1000. Does that mean that the design for the divider changed?
Okay, I'm giving you a general formula. There is some general formula. One is that this feedback, we can divide this feedback divided by the reference frequency. If we divide this frequency by this frequency, then we'll find an integer value, and we'll find what should be this divider there. And we can design this divider. We are familiar with D flip-flop. We can design this divider using D flip-flop. A flip-flop, this is also an important topic. Let's say it can work like a register. I mean, it can store some value. You can study about also D flip-flop and latch. There's also an interview question. What is the difference between D flip-flop and latch? The basic difference is that in flip-flop, it works depending on the clock. If there is clock, then this flip-flop work. On the other hand, latch, it only depending on the level. Level means if it is a clock, the flip-flop are working in the edge, either positive edge or the negative edge. But the latch, it is working in this level, high level or low level, depending on the design. And therefore, flip-flop are using in sequential circuit. Sequential circuit means where we need clock. However, for latch, we need the combinational circuit, where there is no clock. This is the basic difference. Any more question? Nothing?
Actually, I have a question.
Mhm.
So for the design of the entire PLL, which is a little, do what exact components do you need except resistors, capacitors, transistors of certain kind? I mean, probably some breadboard wires, voltage supply, probably need a function generator, oscilloscope, just to measure stuff. What else do you need?
No, I'm telling you, you can design it in Cadence software.
In Cadence, okay.
Okay, in Cadence software, how to design this one using transistor.
Right.
Okay, not in PCB board.
Well, I'm just curious if it's possible to do it physically, like with, say, introductory electronic components.
Yeah, introductory, I believe that you can search if there is an IC or something that can work this job, then you can connect this
Right.
and work this.
Right.
But as an VLSI design engineer, your job would be not using the component.
Right.
I mean, how to make this one?
Right.
Yeah, this one.
It's most like simulation, right?
Yeah,
Rather
most of the
than-
simulation
rather than
type of
actual
thing.
physical.
Oh, okay, one more point I want to show.
Yeah, okay, let me just speak.
I don't know why it turned off. It shouldn't.
Okay. Okay, whatever I discussed right now, you can see this is the differential here, and this is the folded cascade, and you can see this source. This is the tail current. Whatever I'm shouting right now, this is the tail current source, and this is the differential there, and yeah, this is some two current mirror. This is not two-stage open. Whatever I discussed, this is another architecture. It is folded cascade op-amp. This is the folded cascade op-amp, and you can see this is a current meter, this is a current meter here. Yeah, and here this is a current metering, and the performance of the entire circuit. If you are working as a lab design engineer, that you have to, there is some matching. I'm showing you some matching example. Let's say it is a physical layout, I mean layout of the circuit, but what is the matching? Okay, first you can consider this small circuit in here. If it is a current meter, let's say you can see there are 1, 2, 3, 4, 4 blue devices and 1, 2, 3, 4 red devices. So there are some common matching. Let's say A, B, B, A, B, B, A, B, A, B, B. This is a matching, and you can see there is no mismatch. In simulation tool, there are something that you can find, is there any mismatch or not? So you can study about common centroid matching as well as one more matching, common centroid and interdigitized type matching, where you will find these types of matching structure. And without any matching, your circuit will not work. Whenever it will fabricate it, it will not work due to the noise. And you see, this is NMOS differential pair. Here you can see that, just consider this edge. You can see 1, 2, 3, 4 red, 1, 2, 3, 4 blue. And the same in this side also, right and left. As well as if you count the red and blue number of transistor, you will find same number of transistors is here in every line. And if you use symbol, it's like a checkerboard pattern. It's like a checkerboard pattern. Let's say you can see 1, 2, 3, 4. Just consider this 4 line. 1, 2, 3, 4. 1, 2, 3, 4. Then if you fold it like this, it will overlap each one. If you can assume it's a book, and if you can folding it like this, it will overlap with each one. If you fold it up like this 4, okay, this red will go there, this blue will go there. It's the different types of matching. You can study it. I know by saying this, you may say, oh, it's terrible, it's difficult. It's not difficult, it's a matter of practice. But yeah, in the layout design, you used to ask in the interview that, okay, draw a structure of an twisted yoga. They will ask you, draw any structure. You can ask, and you can draw any structure. And then they will tell you, okay, now do some matching for me. Let's say, do some differential pair matching. Then you have to use this knowledge, common centroid and interdigitize, and you have to write in paper and pencil, and you have to show them, okay, I made some matching there. Yeah, this is also some current mirror matching. It's really weird, but you can see there is some mismatch. There is understood, but there is 0% mismatch. This mismatch means whatever the tool doing, they are assuming a center in this block, and from the center of this block, it is assuming that some x and y distance, and it should be same. I know it looks weird, but don't worry about this. Just only study on the basics, whatever I discuss, because to get a job, you do not need like this. I'm just showing you. You have to a clear basic idea, which helps you to get the job. And however you will get the job, you will go to the industry, and day by day you can learn everything. Okay. Thank you everyone for coming here. And if you want, I want to discuss one more point, because I think that most of the students, they don't know how the MOSFET work. Yeah. You can turn on the light when they yes. This is very basic. You can search also online, or you can see some animated video. They will show some animation, then you can find it easily. But I'm talking about some basic idea. Let's see. It is a 2D view of a transistor. It has a drain, it has a source terminal, and it has a gate terminal here. And here it is silicon dioxide. As I mentioned that due to this silicon dioxide, there is no current flow through this gate terminal. This is the gate. Okay. This is the drain, and this is the source. Okay. Let's talk about NMOS. If it is NMOS, then this entire thing is called the body. The body of NMOS is in PMOS. The body of NMOS in PMOS. The body of PMOS in NMOS. It's just so. And as I am designing an NMOS, this drain terminal, you know what is doping? That is periodic table. In periodic table, you can search that there is some doping. In doping, you know, MOSFET from silicon. MOSFET from silicon. In silicon, without any doping, there is no electric flow. to get an electrical flow very well, we need to doping here. It's mean now there is some electron, and it is in P plus. So now, first of all, let's say my source is connected to 0 voltage, and yeah, let's say it is connected to a positive voltage. And when I applied a positive voltage here, let's say I applied positive voltage 0.2 volt, then, and let's say the threshold voltage, there are a couple of assumptions you have to do. Let's say that my threshold voltage is, let's say, 0.5 volt. So if I apply there 0.2 volt, threshold voltage is 0.5 volt, this MOS is off. There is no current flow drain to source. Current flow means there is no current flow in their drain ID. Then if I gradually increase this voltage, and whenever it is just greater than 0.5, my transistor will be off. Sorry, my transistor will be on. And in this situation, there is accumulating some electron. And whenever this voltage is in such a condition, whenever it is VDS greater than or equal to VGS minus VTH, then there is a channel. There is a channel, and electron is flowing from here to here. And it is the control of my gate. And this terminal is connected to 0. The body of NMOS is connected to 0 voltage, and the body of PMOS is connected to higher voltage. Don't be confused. Just remember something like that and go home and study, then you can understand it easily. But before go there, please study about PN junction. How when PN junction work, then you can understand it easily, because the idea of MOSFET comes from PN junction. In interview, sometimes they also ask about to draw this curve. This is the diode characteristics curve. After a certain point, if we make it clearly, after a certain point, whenever the diode is on, then there is a huge current flow through the diode, and typically we can assume this is 0.7 volt, and in the diode there is no current flow in reverse direction, but still there is a limitation, and after some point there is a huge current flow, which means my circuit is gone. I think that this point is known as avalanche breakdown. Okay, so these points are also very important, because these are the very basic. If you carefully remember, forget about this term. Just consider this curve. I also show this curve to you for the MOSFET. If I keep VDS constant, and if I vary the VGS, then there is a curve like this. Whenever I am mentioning about the BGM, sorry, the transconductor is only GM. So these are the basics you have to study. Yeah, it's for me. And if you have any question, you can ask. It's good. Yeah, this presentation would be effective if you study the basics, whatever I mentioned there. And I'm telling you about some books. I'm showing you about this. I think I have these books. If you want these books, I can send him, then he can send you. These books are really
Yeah, I'll show everybody through email. So. Is it a presentation?
Yeah, this is
Yeah, I'll do it.
Okay, then I will send these books to you. It will be helpful for you.
All right.
Okay.
Thank you so much. Thank you.